The exhaustion of fossil fuels and above all the obvious effects of climate change have given rise to an increasing interest in the search for more ecological and efficient alternatives for the production of energy. As a result of this research endeavour, in 2005, in collaboration with the University of St Andrews in Scotland, a new material was designed and manufactured on the nanometer scale, capable of generating 1.2 volts in clean devices similar to the batteries that we know today. These devices, called fuel cells, operate using hydrogen and oxygen and only produce steam as waste. This discovery, reported in the journal Nature in 2006, was the origin of the Nano and Microengineering of Materials group at the University of La Laguna. Since then, the group has been able to discover new materials that have been patented, and at the same time we have steadily incorporated new microstructural control methods for these materials. The problem arises when working at a minute scale, for example below the thickness of human hair, about 80 microns. In these conditions, the microstructural control becomes a complex undertaking, which generally demands the use of relatively expensive equipment. This is where the additive manufacturing technology comes in particular 3D printing of materials that allow for the rapid and economical production of complex microstructures made of the material we want to produce. The work carried out in the context of the 3D printing of nano and micromaterials in our research group is relatively new, but there have been interesting results over the last 2 years. We always try to involve students so that they can develop their final degree projects on research topics of this degree of relevance. In fact, the first result of the research group had its origins in a final degree project. This was the design and assembly for the first time in the University of La Laguna of a 3D printing system by using only a simple beamer for presentations, making it a system that is affordable to all. This initial finding has helped us to acquire and optimize different types of 3D printers, used, for example, for the design of nanomaterial prototypes, for the storage of hydrogen, as a part of the European project EDEN of the 7th Framework Programme. More recently, in July this year, the group has been able to print for the first time 3D biomaterials by using visible light from a simple projector, thereby avoiding harmful UV radiation for the possible manufacture of 3D biostructures with cells incorporated within them. From the outset, one especially clear objective has been to control the form or structure of materials with energy and environmental applications, while preserving maximum detail at minimal cost. The higher the level of detail or resolution we can obtain, the greater is our control over the properties of the materials to be manufactured. For example, the effectiveness of an energy material can be simply improved by increasing its surface. That is, we can obtain more energy with the same material, but through the 3D process, they will be more compact. The problem is that in the scientific field, obtaining structures at a nanometer scale requires considerable financial investment. That's why we use 3D printing of materials as an alternative, so that we can manufacture them in a quick, economical and efficient way. Today, it is expected that 3D printing technology will benefit many sectors, such as energy, nanotechnology, civil engineering, spatial technology, environmental science, cookery, and so on. For example, as regards medical applications, it's possible to print 3D models of organs which could be manipulated by surgeons to plan complex surgeries. Some hospitals have even started to use 3D printing of metallic or plastic parts that will be used in implants and reconstructive surgery. 3D technology allows for the manufacture of new fossil fuel devices which are more efficient and allow for the mitigation of the effects of climate change, since the batteries don't produce pollution and are silent. Their only byproduct is ultra-pure water that could also be used in combination with Canary Islands water containing dissolved salts. The search for alternatives to traditional fuels would also be supplemented by obtaining biodiesel and green diesel, the production of which is to be improved by manufacturing 3D specific catalyzers. The 3D printing methodology we currently use consists of several steps. The first is the digital design of the object to be printed. In general, any CAD software could be considered valid, or alternatively, we could use a 3D scanned image. Once we have our 3D model, we only need to choose the printing material. These could be metallic, ceramic, or plastic. The type of 3D printer determines this decision. It's common in all cases that the formation of the object will be carried out by overlapping layers. These are differentiated by the way in which those layers are deposited and fixed, for example, by means of plastic fusion, or an organic adhesive, or laser, and so on. Once the 3D models are built, we carry out checks that the product materials have the properties required from the beginning, that is conductivity, catalytic and photocatalytic properties, and so on. The range of possible applications of 3D printing technology is huge. Almost any area that comes to mind can use 3D printing, and every day we see the arrival of new applications that use the technology. In our research group, we're focused on improving the production of clean energy, and for that purpose we have to be capable of improving the resolution of 3D printing. Regarding the biomedical applications, there are challenges for the future, such as achieving the deposit of living cells onto biodegradable frame or the creation of blood vessels, but nowadays significant steps have been taken in these directions. That's why we hope to go on working on 3D printing, opening up new and exciting possibilities in the future.